Welcome to AI Paper Slap. Today we are dissecting a paper called DOPD, Dual On-Policy Distillation by Xin-Lai Yu and a team from NUS, CUHK, PKU, and JD Explore Academy. Let's get straight into the core insights.
Yeah, let's just dive right into it.
So on-policy distillation, or OPD, usually hits this hard performance ceiling. And to break through, researchers try giving the teacher model privileged information, right? Like verified reasoning hints or visual bounding boxes.
Right, to boost the signal.
Exactly. But this actually causes a massive failure mode called privilege illusion. The student just mimics the unlearnable hints instead of acquiring real capability, which leads to entropy collapse. DOPD fixes this by dynamically routing token-level supervision using something they call a privilege advantage gap.
Yeah, which is super clever.
It applies entirely different strengths of distillation based on whether a token actually has transferable capability or if it's just privileged noise. And the result is, honestly, a massive performance leap for both large language models and vision language models.
It really is.
Yeah.
But to truly grasp the mechanics of this DOPD framework, you kind of have to look closely at the baseline setup it's trying to repair, right?
Yeah, absolutely.
So in standard on-policy distillation, you take a weaker student model and you supervise it using a stronger teacher model. But the critical detail for everyone listening is that this supervision happens on trajectories generated by the student itself.
Right, the student generates its own rollout.
Exactly. The student rolls out a sequence of tokens, and then the teacher provides supervisory signals on that specific sequence to sort of correct it in real time.
Which makes sense. I mean, it's the dominant post-training paradigm right now because it explicitly mitigates distribution shift.
Yeah, 100%.
The student isn't just blindly pulling gradients from static offline data that it would never naturally generate on its own. It's actively learning to correct its own specific distribution of outputs.
But for the ML engineers tuning in, the instinct is always to push the boundaries, right?
Yeah.
Like if standard OPD works well, the immediate thought is to artificially inflate the teacher's IQ.
Oh, of course. Give it a cheat code.
Exactly. We give the teacher privileged information during training to generate a theoretically perfect signal. And the paper highlights some very realistic, common ways we do this.
Like the Math 500 stuff.
Yeah, exactly. If you were training an LLM on complex Math 500 tasks, you might inject verified step-by-step reasoning hints right into the teacher's prompt.
You don't give away the final answer, though.
No. But you lay down a structured path for the teacher to follow. Or, if you are working in the multimodal space with vision language models, you might hand the teacher exact object bounding boxes.
Right, or like quadruple coordinates before asking it to describe an image.
Right. So on paper, the teacher's prediction distribution suddenly looks vastly superior.
But this introduces the core failure mode the authors identified, which is that privilege illusion, because we are conflating two entirely different phenomena in the loss function here.
Yeah, it's a dangerous mix-up.
The first is the intrinsic transferable capability gap-like, the actual reasoning logic that the student can and absolutely should learn.
Right. But the second is the information asymmetry gap. And this gap exists purely because the teacher has the cheat sheet and the student doesn't.
Which becomes fatal, honestly, because the student will never have access to those hints at inference time.
Never.
When you force the student to minimize the KL divergence between its output and the privileged teacher's output across every single token, you're literally forcing it to memorize the byproduct of information it can't even see.
If you're trying to picture the real-world impact of this conflation, think about a junior developer, so our student model, trying to learn by watching a senior developer write code.
Oh, that's a great analogy.
Right. But the senior developer is secretly using Stack Overflow on a second monitor. So the senior dev is pumping out flawless, highly optimized code, and the junior dev is just watching the keystrokes.
Just trying to mimic the syntax.
Exactly. Because the junior can't see the Stack Overflow page of privileged information, they aren't actually absorbing the architectural logic or the deep reasoning behind the code structure. They just desperately try to memorize the final output. And we know exactly what happens to that junior developer when they actually get the job and the internet goes down. They freeze.
Totally.
In machine learning terms, that freezing is entropy collapse. And the paper's training step graphs illustrate these beautifully under the hood. When a student indiscriminately distills from a privileged teacher, the student's softmax distribution becomes unnaturally sharp around these shortcut tokens.
The probability of alternative valid reasoning branches just gets pushed to near zero.
Exactly. The model literally forgets how to guess or explore. The entropy of the model just flatlines, exploration dies, and the entire distillation process fails.
You end up yielding marginal or even negative late-stage performance gains compared to just vanilla OPD. So clearly, the researchers needed a way to separate the signal from the noise here.
Yeah, they needed a mathematical lie detector, essentially.
Right, to figure out if the teacher's confidence on a token comes from genuine reasoning or if the teacher is just, reading off the hidden monitor.
And they engineered an incredibly elegant metric for this. They call it the privilege advantage gap, which is denoted as script A in the paper.
Okay, so how does script A actually work?
To calculate this gap for any given token, they instantiate a privileged teacher, so the teacher with the hints, and a privileged student.
Wait, a privileged student?
Yeah, the privileged student is just a copy of the student model that is temporarily granted the exact same hints as the teacher. Then, they measure the absolute difference in log probabilities between those two models when predicting the next token, given the identical privileged input.
Oh, that's smart. Because by giving the student the hints just for this calculation, you've completely neutralized the information asymmetry.
Exactly. Both models have the exact same context now.
So, if there is a massive difference in their predictions, it cannot be blamed on the hints. A large gap means there is a fundamental architectural capability gap between the teacher and the student on that specific token.
Yes, it's a pure capability signal. And conversely, a small gap means the teacher was mostly just coasting on the privileged information.
Which brings us to a crucial structural insight from the paper, which is this idea of token-level non-uniformity.
Right, because not all tokens are created equal.
Exactly. When a model generates a massive chain of thought rollout, the actual thinking isn't smeared evenly across every single word.
Not at all. Only a very small subset of tokens actually encodes decisive branching logic or grounded evidence or, critical reasoning.
Yeah, the vast majority of the tokens are just grammatical glue or obvious transitions.
Right. Therefore, in conclusion, stuff like that.
But I imagine a lot of practitioners listening right now are kind of rolling their eyes at the idea of micromanaging loss at the token level.
Oh, for sure.
Because standard distillation just blasts the entire sequence with a cross-entropy loss function and just lets the optimizer's backpropagation sort out the weights. Is filtering token by token actually worth the computational overhead, or is this just theoretical hair splitting?
It is absolutely moving the needle.
Yeah.
And the authors actually anticipated that exact skepticism. They came back with a devastating ablation study.
Oh, I love a good ablation study. What did they do?
They designed a test where they selectively dropped 20% of the tokens during training, meaning they applied zero distillation loss to them.
Okay.
If you drop 20% of completely random tokens, the final benchmark performance barely deviates from vanilla OPD. If you drop the 20% of tokens with the lowest advantage gap, again, almost zero performance impact.
Meaning those low gap tokens were basically useless for capability transfer anyway.
Exactly. But if you remove just the top 20% of high advantage tokens, the golden tokens identified by that gap metric, the overall performance gain of the LLM is slashed in half.
Wow, slashed in half just from 20% of the tokens.
Yeah, and in the vision language model experiments, the results were even more extreme. Dropping those high advantage golden tokens reduced the performance gain down to a mere 20% of what vanilla OPD achieved.
That is wild. That proves definitively that the vast majority of actual learnable capacity transfer is heavily concentrated in specific branch points of the sequence.
Yeah, if you miss those golden tokens, you've basically wasted a training run.
Which perfectly sets up the core mechanical engine of the paper, right? DOPD's dynamic routing.
Yes, this is where it all comes together.
Once they calculate the advantage gap for a token, they compare it against the predicted probabilities of the student denoted as QS and the teacher, QT, and based on those three variables, they dynamically route the supervision into 4 distinct training regimes on a token-by-token basis.
Let's actually trace a token through this routing system to see how the gradients get updated. The first scenario is the jackpot.
The golden tokens.
Right. You hit a crucial reasoning step where there is a high advantage gap and high teacher confidence. The teacher knows exactly what the next token should be, and it's driven by a genuine capability advantage.
For these golden tokens, DOPD applies what they call deep teacher distillation. And the specific math they use here is fascinating.
It really is.
Instead of standard KL divergence, they apply a full vocabulary Jensen-Shannon or JS divergence to aggressively transfer the teacher's capability.
The choice of JS divergence here is a vital detail for the implementation. Because in standard distillation, you typically see forward or reverse KL divergence.
Hmm.
Forward KL is mean seeking, right? It forces the student to cover all the modes of the teacher, which often leads to this smeared, overbroad distribution where the student just starts hallucinating.
And reverse KL is the opposite. It's mode seeking. It forces the student to pick the single highest peak of the teacher and ignore the rest.
Exactly, which means it loses all the subtle nuance of the teacher's alternative thoughts.
And if you look at Table 7 in the paper, they empirically prove that JS divergence outperforms both of them for full vocabulary alignment in this specific high gap setup.
Yeah, because JS divergence is symmetric and bounds the divergence. It balances support coverage and mode concentration.
Mechanically, this allows the student to pick up the teacher's dominant token choice, but also its secondary and tertiary preferences across the entire, 100,000 token vocabulary without smearing the primary mode. It captures the full shape of the teacher's reasoning.
Super elegant. So, moving to the next scenario, what happens when the model generates the connective tissue of a sentence? You have a low advantage gap, but high confidence for both the teacher and the student.
Like they both know the word therefore comes next.
Right, this is just consensus knowledge. Enforcing full, heavy-handed JS divergence here is a massive waste of compute.
Yeah. Worse, it risks over-penalizing the student for microscopic deviations or forcing it to memorize privileged shortcuts that don't even matter.
Exactly. So DOPD downshifts to light teacher distillation here. They drop the full vocabulary JS divergence and instead use a top K reverse KL divergence.
Which makes sense. It softly absorbs any mildly useful knowledge from the top predictions without aggressively forcing the weights to shift.
Then you hit the messy part of the rollout, a scenario with a low advantage gap and low confidence for both the teacher and the student.
The blind leading the blind.
Exactly. Neither model really knows what the next token should be, and there's no underlying capability gap to exploit. If you force the student to imitate the teacher here using standard loss, you are actively injecting noisy, misleading gradients into the network.
You're literally forcing the optimizer to confidently update weights based on a guess.
Right, so DOPD switches to weak student regularization,
Right.
and they do this using a stop gradient on the privileged student.
Let's explain the mechanics of that, actually, because it's brilliant. By placing a stop gradient on the privileged student's output, you essentially sever the computational graph for that specific tensor.
Exactly. The target distribution becomes a fixed, frozen anchor. The system completely stops listening to the privileged teacher for this token.
Right.
Instead, the loss function just pulls the deploying student's distribution toward its own privilege baseline. Because the gradient can't flow backward through the anchor, the weights of the network are prevented from drifting wildly toward the teacher's noise.
It essentially tells the optimizer, just stay consistent with yourself right here and don't make any aggressive updates.
Yeah, precisely. Which brings us to the final routing category. High advantage gap, but high student confidence.
So the student is very confident about its path, but the teacher is lost or unconfident.
Right. In standard distillation, the loss function would basically obliterate the student here. It would penalize its confidence and forcefully pull its weights back to match the teacher's uncertainty.
But DOPD recognizes that in long, complex rollouts, the student might have actually found a valid, alternative local reasoning branch that the teacher just didn't explore.
Yes. So to avoid crushing that valid exploration, DOPD applies light student distillation. It uses a top K reverse KL divergence, again targeting the privileged student as the anchor, just to softly encourage self-consistency without penalizing the student's unique discovery.
So you step back and look at the whole system. It's an incredibly nuanced surgical routing mechanism.
It really is.
Deep, full vocabulary JS divergence for the golden tokens, light touches for consensus, and strict stop gradient self-regularization to block the noise.
Right, but obviously the ultimate test for any ML architecture is whether this mechanical complexity translates to actual benchmark domination.
Well, the raw numbers from their experiments are staggering. They ran this across 8 LLM benchmarks, including Math 500, Amy 25, and LiveBench, and 8 VLM benchmarks like MMStar and MathVision.
Yeah, and DOPD systematically crushes vanilla OPD across the board.
Looking at the Quen-3 model specifically, when distilling from the massive Quen-3 8b down to the 1.7b model, DOPD achieved a 12.3-point gain on average.
Which is huge.
It recovered an astonishing 89.8% of the original performance gap between the teacher and the student. And in the multimodal space, transferring from Quen-3 VL8b to the 2b model, it generated a massive 6.0-point bump over all the baseline.
Those numbers are undeniably impressive, but we kind of have to address the practical engineering reality here.
The compute cost.
Yeah. To calculate that privilege advantage gap dynamically, you have to run a privileged student forward pass, a privileged teacher forward pass, and a standard student forward pass for every single token sequence.
Yeah, the computational overhead of running 3 parallel forward passes is a massive hit to the GPU cluster.
Oh, absolutely.
The AWS bill alone would make most engineering teams hesitate. Is the return on investment actually worth that much compute per step?
Well, the authors are entirely transparent about that limitation. It does require significantly more compute per step than vanilla OPD. However, they demonstrate two massive ROI factors that justify the cost: extreme scalability and robustness against catastrophic forgetting.
Okay, let's look at scalability first.
Right. When you have an extreme capacity mismatch like distilling the Quen-3 8b model all the way down to the tiny 0.6b model, vanilla OPD completely breaks down.
Right, because the 0.6b model just doesn't have the parameter budget to blindly absorb the massive teacher's entire probability distribution. It hits a brick wall and only manages to gain, what, 3.5 points in that setup?
Exactly. But DOPD thrives in that exact same scenario.
Really?
Yeah. Because it selectively filters the gradients, routing only the highest signal, most crucial capability tokens to the optimizer, it managed a 14.1-point gain on that tiny 0.6b model.
Wow, so it uses the student's limited parameter budget with surgical efficiency.
Precisely, which alone justifies the extra forward passes if you were deploying to edge devices,
Definitely. But the second ROI mitigating catastrophic forgetting is where the routing system really flexes. One of the biggest unsolved problems with post-training paradigms like GRPO or supervised fine-tuning is that when you train a model on new reasoning data, it aggressively overwrites its previous weights.
Right, it suddenly forgets how to code or answer general knowledge questions.
Yeah, and the authors tested this by training the model sequentially, first on general data, then on reasoning data, and finally on coding data. Standard GRPO exhibited massive catastrophic forgetting.
Yeah, the model's general and reasoning benchmark scores just plummeted the moment the coding training started.
Vanilla OPD fared a bit better, but still severely degraded. DOPD, however, maintained its high performance across the board.
And if you think about the mechanics we just discussed, it makes perfect sense why.
Oh, because of the routing.
Right. When the model is learning new coding tokens, the previously learned reasoning concepts will naturally exhibit a low advantage gap and high student confidence.
Oh, wow. Yeah.
The dynamic router sees that and throws those specific tokens into the light or weak regularization regimes. It effectively shields those stable weights from aggressive gradient updates, allowing the network to learn new coding skills without overwriting its reasoning foundation.
It's a mathematically elegant way to protect old knowledge while acquiring new skills.
It really is.
So, summarizing this for you listening today, DOPD proves that in the modern era of post-training, uniform data blasting is just a dead end.
Yeah, completely.
Treating every token in a sequence as equally important and assuming every teacher advantage is a learnable capability leads directly to privilege illusion and entropy collapse. Adaptive, token-wise routing based on privilege advantage gaps, isolating those golden tokens, is the definitive future of squeezing massive reasoning capabilities into highly efficient edge models.
And that framework leads to a really profound implication that builds directly on the paper's findings.
Oh, like what?
Well, think about it. If this DOPD architecture can mathematically isolate the exact tokens that represent genuine learnable capability versus mere information asymmetry during post-training, could we apply this exact same gap metric in reverse to automatically curate and prune massive pre-training data sets?
Oh, wow. That is a fascinating concept. So instead of applying the advantage gap during the fine-tuning stage?
Exactly. If we can run a quick lightweight pass to find the exact golden tokens that a target architecture actually needs to learn from, we could potentially filter out the vast oceans of noise and unlearnable slop in raw web scrape data before the massively expensive pre-training run even begins.
We could define data quality not by arbitrary human standards, but by the mathematical learnability of the neural network itself.
A completely targeted, model-specific data pruning pipeline driven by the advantage gap.
That could fundamentally change how we approach dataset curation at scale. That is definitely something to seriously mull over. Keep pushing those boundaries, keep questioning the baselines, and we will catch you next time on AI Paper Slop.